Everyone. In chapter 5, we'll be deepening our knowledge on what we've looked at in the past couple of weeks regarding properties of solids and fluids. And when we talk about fluids, we are referring to gases and liquids. And if you remember, looking at different fluids, we looked at the real fluids and we've also dealt with ideal gases. Let's start by looking at the typical kind of equations you'll be provided when you need to work out some examples. Secondly, I also want to emphasize the PV relationships that we've looked at in the past couple of weeks under different processes. We've seen polytropic, isobaric, isochoric, isothermal, and isentropic. Take note of for the first one, polytropic, we've talked about the fact that for your polytropic, P1V1 raised to power n equals P2V2. We've also shown the fact that your P1V1, your PV rather, is equal to constant. So we've dealt with that. And then under isobaric conditions, we've said that that is the condition where your pressure is constant. So take note, for example, if we pick under in the y-axis, if at this point of pressure, you see that the volume has changed from V1 to V2 while the pressure remains the same. And for isochoric conditions, we said that is when your volume remains constant. So hence, if we pick a volume point here, we can have a volume point and we have our pressure changing from 1 to 2. So that is for your isochoric. And for isothermal, we've said that what is important in under that condition is that your temperature remains constant. Hence, P1 changes. Your P rather changes and your volume also changes. And then for isentropic, you could see that your isothermal and isentropic are similar. We emphasized that in the class the last week and then in the previous classes. Another thing I want you to take note in all these PV diagrams is the magnitude of the work done. Magnitude of the work done. I want you to look at the area. Look at this area. You see the area that is shaded. Look at the work done. See the work done here different from that and different from this and here. And you see it's only under isochoric condition that no work is done. So under isochoric condition, and for all these conditions you've also been provided. So these are the equations will be encountering in different calculations. You typically be provided these calculations. So what is left of you is to be able to decipher by looking at the questions that what equation will be appropriate. So you've also been given equations for the work done, equation for change in internal energy, and your equation for your heat transfer. So you've got that, and then you have for your enthalpy change. So we've got all those equations provided. Let's look at the first example. We look at the example. As usual, we want to start by looking at what we've been given and what we are looking for. So the known and the unknown, so that we can move from known to unknown. So 0.23 kilogram of oxygen. So that is mass has been provided. 0.23 kilograms at a pressure and temperature of, so for our pressure it's 110 kilopascal, and then we've been given a temperature which is 25 degrees C. Remember, we've said whenever this temperature that shouldn't be K. See, remember we've said that we always need to watch out for consistency of values, consistency of units rather, and then our question is to look for R. That's what we're looking for. And if you remember, whenever we are dealing with R, the unit, there is a K in there is Kelvin in the unit. Hence, this needs to be converted to Kelvin. That will be 225 plus 273. which gives us 298 Kelvin. Further, we've emphasized the fact that whenever we are dealing with this kind of questions, our temperature should always be converted to Kelvin. Another thing I want you to take note of, which will be necessary as we move forward, is the different units of your pressure. One, take note of the fact that 1 kilopascal is same as 10 raised to power 3 Pascal. We'll see more as we move on. Further, 1 Pascal equals 1 Newton per meter squared. And then 1 Newton meter is same as 1 Joule. It's essential to take note of this so that whenever as we deal with our calculations, we can convert the units appropriately. For example, looking at this, we have a volume in meter cube. So if you have a volume in meter cube, it is essential to convert our pressure into a unit that has meter in it. So let's move on. And also, seeing what we've been given and what you're looking for, it should easily come to mind that the equation we'll be using will be PV MRT. PV MRT. P pressure, V volume, M mass, R, this is what we're looking for, and T temperature, which we've been given. So if we make R the subject of the formula, we should have PV over MT. So then our R becomes, let's plug in all the formula, let's plug in all the values we've been given. So we have our P, which is 110. Remember, as I said earlier on, it is saying let's first convert our pressure to a unit that has meter in it, so we can easily bringing all this together. We can easily say 110 kilopascal is same as 110 times 10 raised to power 3 Newton per meter squared. Newton per meter squared. If we plug that in here, times 10 raised to power 3, let's put in the units so that we can see if we are consistent. And then the V, 0.165 meter cube. We've been provided the volume divided by our M. We've been provided the mass, 0.23 kilogram. And then we have the temperature, 298 Kelvin. This will cancel out, and then we are left with an M here, and then we have a Newton there. If we do that, we should have 18150 Newton meter over 68.54 kilogram Kelvin. So if you remember, Newton meter is same as joules. So that is 18150 joules divided by 68.54 kilogram Kelvin. So our R then becomes 264.8 joules per kilogram Kelvin. This can also be rewritten as 0.265 kilojoules per kilogram Kelvin. Kilojoules per kilogram Kelvin. So that is our answer. So let's look at another example. A vessel of volume 0.3 meter cube. So we have our volume 0.3 meter cube contains air. We have our R value 294 joules per kilogram Kelvin at a pressure of 35 kPa. So we have a pressure of 35 kPa, kilopascal. And remember what we saw earlier on, once we see our volume in meter cube, the first thing we want to do is convert this into unit that has meter in it. So our 35 kilopascal becomes 35 times 10 raised to power 3, the 10 raised to power 3 from the kilo, Newton per meter squared. So we've got that. At a temperature of 16, so 16 degrees C will be 273 plus 16, which is 289 Kelvin. 289 Kelvin. So we've gotten that. Atmospheric air leaks slowly into the vessel when the pressure of the air in the vessel has risen to. So that shows us that we have another P. So we can then call this P1, and then we say we have P2, 65 kPa. It's has risen to 65 kPa, the leak is stopped. The temperature of the air in the vessel is then 50 degrees C. So it is evident that at temperature 2, we say this becomes T1, and then we have T2, 50 plus 273. So we have that, which gives us 323 Kelvin. So determine the mass of air which has leaked in. Take note of that, as leaked in, the pressure of the vessel when it's content. So let's start. So we are looking for a mass. We are also looking for a pressure. All right, so I haven't been given all those values. So it's, from what we've seen, it is evident we have two P's. It is evident we have two V's. So from there, we can then start by saying P1, V1. So using the same unit, the same formula we used earlier on, M1 R T1. So remember, R is a constant. So even when we have P2, V2, the R will still remain the same. So from here, we can say the first thing is we're looking, we first calculate, start with the first mass, P1, V1, R, T1. So if we plug in the values we've been given, 35 times 10 raised to power 3 Newton per meter squared, multiplied by 0.3 meter cube, divided by our R value, 294 joules per kilogram Kelvin, 289 Kelvin. So remember, this is per kilogram Kelvin. So this is 1 over Kelvin here. So this should cut that out. So that should cut that out. This should cut that out. And then we should be left with an M there. So if we continue in that line, it becomes 10,500 Newton meter divided by 84966 joules per kilogram. So remember, we've also said Newton meter is same as joules. So if we, that 84966 joules per kilogram, so that cuts that out, and then we are left with our kilogram value. We are left with our kilogram value, which will then be M1. So take note of that, 0.1236 kilogram. So we have an M value. But remember, we said we're looking for the final mass. That's the question, the mass of air which has leaked in. So we are looking for the amount that has leaked in. So let's calculate the final mass. So remember, we have two P values. From what we've seen, we have two P values, we have two T values. But in terms of the volume, because in as much that air has leaked in, the volume, the vessel hasn't changed. So if the vessel hasn't changed, the volume remains constant. So the volume remains constant. So let's calculate our M2. So we want to calculate our M2. We've been given the P, we've been given the P, we've been given the T. So we can then, using the previous formula again, we have P2V2 equals M2 R T2. Remember what we said earlier on, R is constant, so nothing is changing there. So our M2 will be equal to P2V2 R T2. So we just plug in everything we've got. 65 times 10 raised to power 3 Newton per meter squared times 0.3 meter cube divided by 294 joules per kg Kelvin multiplied by 323 Kelvin at T2. That cancels that out, this cancels that out, we are left with an M there. So that gives us 19500 Newton meter divided by 94962 joules per kg. Remember, we've said this is joules. So if this is joules, so joules will cancel out that. And then we should be left with M2 equals 0.2053 kilogram. So that is our M2. We have M1, we have M2. So remember, so the mass of the air in the mass of the air in the vessel has increased. So now we want to know if the mass, since we know we started with M1 is 0.12, our M2 is 0.20. So you can see there's an increase in mass. So obviously the difference in the two will be the amount of air that has leaked in. So our A would then be mass of air leaked in will be equal to final mass minus initial mass, M2 minus M1. So 0.2053 minus 0.1236, 0.0817 kilogram. The B question is the pressure. Let's quickly check our question again. The pressure in the vessel when its contents have cooled to 16 degrees C. So remember, the process continues. So if it's a continued process, so that means if we go back to using at our equation of MRT, so our M now will be M2. So our M at this point will be M2. So if we plug in, as we are looking for P, then MRT over V. So we have our M will be, we've said our M will be M2, 0.2053. Remember, the mass has changed. And then we've got the R294 joules per kg Kelvin. And then remember, the temperature is 16 degrees C, which is 298, 289 Kelvin. So if we plug that in, 289 Kelvin divided by 0.3 meter cube. So it should give us a value of P as 17. So remember, let's cancel out so kg cancels out there, Kelvin cancels out there. So we should be left with our Newton meter and then our meter cube. So remember, joule is same thing as Newton meter. So we should be left with 17443.52 Newton meter or joules divided by 0.3 meter cube. So if we do that, that should leave us with pressure being 58145.07 Newton per meter squared, which is same as 58.1 kilonewton per meter squared, which is same as 58.1 kilopascal. So if you have any query or you need any clarification regarding this, we'll be dealing with that in the discussion forum. Thank you.